Dear student, welcome to the second part of lecture series of Molecular Beam Epitaxy. In the second part of Molecular Beam Epitaxy lecture series, we will discuss about the processing steps involved in deposition of thin film using molecular beam epitaxy. So we will discuss that what are the steps through which in molecular beam epitaxy we can deposit, or we usually deposit, well oriented, textured and directional single crystalline thin films. Dear student, kindly note that most commonly a single crystalline thin film prepared with molecular beam epitaxy are gallium arsenide based. Usually, uh, the microelectronics industry prepare gallium arsenide, and gallium arsenide can be doped with different types of materials like aluminium. So, mostly in microelectronics industry, the MBE is common in for deposition of gallium arsenide or gallium doped aluminium arsenide. So for simplicity of molecular beam epitaxy, we will explain the step-by-step processing of deposition of thin film. Okay, initially in molecular beam epitaxy, we load substrate and precursor inside the chamber of the molecular beam epitaxy. Okay, substrate and the precursor are loaded inside the chamber of the molecular beam epitaxy. Let's explain what kind of substrate and what kind of precursor we need for molecular beam epitaxy. Dear student, please note that substrate is very important. Substrate play a vital role in molecular beam epitaxy because the deposited film is basically orient and are directed according to the direction and orientation of substrate. Usually in molecular beam epitaxy, single crystalline silicon substrate are used, and these substrates have certain specific direction and orientation. The precursor used in molecular beam epitaxy is basically in the form of solid form. Okay, the precursor and the substrate, please note that the lattice mismatch between the substrate and deposited precursor material must be less in molecular beam epitaxy because the deposited precursors must follow the orientation and direction of substrate. If the lattice mismatch between the substrate and the precursor is material is high, there is a possibility that the structure of deposited thin film is damaged, because if the lattice mismatch of the substrate and precursor deposited precursor thin film is more than 10%, dear students, so there will be a stress between the substrate and the precursor based deposited thin film, and this at the interface. So the stress at the interface will cause a damage or tingling in the structure, and due to this, the structure or the deposited thin film on the substrate where MBE will be defect one. So it will be a defected, and the number of deficiencies or the impurities or vacancies in the deposited textured film will be more. So in order to prepare well-oriented and well-textured thin film in MBEs, the lattice mismatch of the substrate and precursor material, which is basically evaporated and deposited, must be less than the 10%. So due to which we can get well-oriented and textured thin film. After loading the precursor and substrate inside the molecular beam epitaxy chamber, the chamber or the reaction chamber is basically highly evacuated. Dear student, please note that the evacuation or the high vacuum used in molecular beam epitaxy is somewhere around 10 raised to power minus 8 to 10 raised to power minus 10 torr. This pressure is too much. Okay, so it is quite difficult to attain the higher ultra high vacuum vacuum pressure. So for this, the in MBEs, since I have already told that there are different types of vacuum pumps like rotary pump, turbo pump, diffusion pump and cryo pump. All those pumps have a limitation, and it is quite difficult to attain such ultra high vacuum. So in molecular beam epitaxy, the combination of all these pumps is used. I will discuss in next part of this lecture that what kind of combination and what kind or what types of pumps are used in molecular beam epitaxy. So in first step, we have loaded the precursor and substrate in reaction chamber of the molecular beam epitaxy devices. Okay. In the second step, the ultra high vacuum is created via a combination of different types of pumps. There could be cryo, turbo, diffusion, or rotary pumps. Okay, so please note that diffusion pump is very less common in the molecular beam epitaxy because of the oil present in that, but we will discuss that what kind of pumps are basically used. Okay, so after creating high vacuum inside the reaction chamber, both the substrate and precursor and dopant, if we want to deposit or if we want to incorporate dopant, are heated. So the precursor and dopant are heated in order to evaporate them, okay? Whereas the substrate is heated and rotated because due to heat and rotation we can get uniform deposited thin film, okay? So the heating temperature used for in MBE for substrate is around 200 degrees centigrade. The reason for heating the substrate is that there is a possibility in an MBE device that is there could be a possibility of any liquid phase impurity on the surface of the substrate. And secondly, with the heating of the substrate, the uniformity of film become more easy. Okay, so due to this, the substrate material is heated and rotated in the MBE reaction chamber. Okay, the dopant and the precursor materials are basically heated and evaporated. So usually in MBE, the dopant is present in effusion cell, okay, and the dopant is basically evaporated and heated via a thermionic emission process, whereas the precursor material is present in a container which is basically heated and evaporated either by thermal evaporation or by electron beam operation. Okay, so in third step, the substrate and the precursor and dopant materials are heated and the substrate is rotated. After heating the dopant material and precursor material and substrate, the dopant and precursor materials are basically evaporated in a controlled step-by-step injection fashion. Okay, so there is a kind of electronically controlled shutter on the top of the containers of precursor and dopant, and they are basically this electronically controlled shutter basically control the evaporation rate of the precursor and dopant. Please note that apart from the evaporation control rate and thickness of the dopant and precursor, the thickness of precursor and dopant deposited or incorporated onto surface of substrate is basically controlled or is basically monitored, not controlled but monitored by a read device. Read is basically reflection high energy electron diffraction. It's basically monitor that how much precursor and dopant are evaporated and transported onto the surface of the substrate. After controlling the rate of precursor and dopant evaporation, the precursor and dopant are transported at the surface of the substrate. Okay, or when the dopant and precursor reach at the surface of the substrate, the dopant and precursor materials start to condensate. Okay, they basically turned into a solid phase. Since you know that the dopant and precursor melting temperature in MBE is high, it's around between 200 to 800 degrees centigrade, whereas the temperature of substrate used in MBE is around 200 degrees centigrade. So due to temperature difference, the dopant and precursor from high temperature zone transported onto the substrate surface, and when they reach to the when they reach to the substrate surface, the temperature of substrate is less than the temperature of the dopant containers. So basically it's the dopant and precursor start to solidify it, and it's become the dopant and precursor solidified, nucleate and condensate and transferred into a single crystalline, uh, a highly epitaxial, well-oriented thin film. The door orientation, as I've earlier discussed, that will depend on the direction and orientation of the substrate. So the deposited, condensated, and nucleated precursor and dopant will follow the direction and orientation of the substrate on which they are deposited. So these are the main four steps which are basically used in MBE in order to deposit the well-oriented textured thin film. And as in first step, the precursor and the substrate are loaded in the reaction chamber. In second step, the high ultra vacuum is created in the reaction chamber. In third step, the a substrate is rotated and the precursor and the dopant are evaporated evaporated, and in the fourth step the precursor and dopant are transported onto the substrate surface, where they are condensated, nucleated and transferred into well oriented texture thin MBE based thin films.